chapter 13. Don't worry about too much for today because it's basically revision from year 9 and year 10 and year 11. So you know year 9, year 10, year 11, all the probability are the same. Like you keep learning the same thing for 3 years. So what I'm going to do for this 15 minutes is revise what you have learned last 3 years. I have listed out all the definitions you are required to know on the first page and include all the formulas you need to know. So I'll just go through all of this. If you have any questions, just ask me. So we use values in between 0 to 1 to talk about probabilities. We talk about chance. Like normally, like students always ask me, do you put in percentage form or decimal or fractions? I'll say if doesn't really matter, but like we don't really use percentage a lot. Okay, you can put in percentage like 60%, that's fine, but we normally say 0.6. Like that's, I don't know why, but like we normally put in 0.6. In fraction form, if your probability is 7/13, some value like that, you can't give exact decimal, so keep that into the fraction form. So keep 7/13. Do not put into your calculator and find the approximate value. You keep things in exact form unless it tells you how many decimals it requires. So this is the domain for probability. You can treat 0 to 1 as domain of probability. I can't think about questions now, like, but there are questions in VCA which, for example, ask you to solve something, like solve for a variable x, but it's a probability question. This x represents chance. And when you solve out that equation you set up, you might get, for example, 1.1, and another answer is 0.5. You won't take the 1.1, you will take the 0.5. You need to remember to reject the incorrect values. Why say this now, like everyone saying, oh, I know probability is in between 0 to 1. But when you actually do probability questions, you can't remember that. So that's, in the examiner report, that question, like everyone lose one, most of people lose 1 mark because they cannot reject the correct values, reject the wrong values. So when you see probability questions, keep that in your mind. 0 to 1 should be your domain, and remember to check your answer after you solve it. And the second one is like, what's a trial? Well, trial is a single experiment. You can do something, you can observe something, that's a trial. An outcome. So an outcome is the possible result of an experiment. So very typical questions like toss the coin. You can have tail or head, they are all outcomes. What is sample space? Sample space is a collection of outcomes. Okay, it's a collection of outcomes, so it's a set. So I will say head or tails in a set. That's called the sample space. Okay, that's called the sample space. And we say sample space, we use this symbol to represent sample space, or we can also use this symbol to represent sample space. When you see the symbol, that means like a full set, like a whole sample space. An event. Event is the list of favorable outcomes, and is the subset. It's a subset of the sample space. Favorable outcomes, it can be something I want to see, or it can be something I'm investigating. So for example, I have a box of chocolate and I know there are white chocolate and black chocolate in it, and I want to see what's the percentage of black chocolate. So black chocolate will be my favorable outcomes, and that can be the event I'm looking for. So that's an event. So equal likely outcomes, but we don't really do equal likely outcomes that much now. Like year 11, yes, we do equal likely outcomes, but now we don't really do much about this. It's the outcome that have the same chance of occurring. Toss the coin, throw the dice, like they're all equal likely outcomes. Okay, so, or something when they can happen with the same chance. Probability of an event in which outcomes are equal likely can be calculated as the following formula. So probability A is the favorable outcome A. That can be calculated in number of A divided by the number of total outcomes. So equal likely, okay, so what's the proportion of your favorable outcomes compared to the whole sample space? So that's the number of A divided by the number of total outcome, but that must be equal likely events. If it's not equal likely events, you can't use this formula. And also that must be discrete random variable. I'll talk about the discrete and continuous more later. But you know, like this formula is, you can use it in very restrict condition. So we don't really use this formula a lot in year 12. Okay, subject probability. The probability is assigned a value just on the basis of experience. I can say for this class, I reckon 90% of the students can get a study score above 35. That's based on my experience. It's not really an experiment from this class. It's based on what I have seen before for my past students. It's not really accurate. Okay, it's not really accurate. It's just something I believe. Okay, I believe for this class. So that's called the subject probability. So it's not that accurate. Therefore, we can actually do experiment for this class and get experimental probability. I give you some mock exam and I see your score, and I base on that one, like based on the experience this class takes, and give a kind of accurate approximation. So that's called the experimental probability. So the experimental probability, or you can call that the relative frequency. Okay, experimental probability and relative frequency, they calculate in the same way. Is the number of favorite outcomes I achieve in this class and over the total outcome. So same way as calculate the equal likely events, kind of the same thing. But you know, always I give this simple example here. When you toss the coin, you know there's half chance to get head and tail, but you toss it 10 times. You're not going to, every time you toss it for 10 times, you get 5 heads, 5 tails. You can get 10 heads, you can get 0 tails. That's possible to happen. But can you say like, oh, your theoretical probability is wrong. It should be 1 to get head and 0 to get tails. You can't predict that, because the relationship between experimental probability and theoretical probability is when you do sufficient large number of trials, then you can say your experimental probability will approaching to the theoretical probability. So you need a large number of trials. You do it 10 times, well, you know something happened, you can do 10 tails, 1 head, no head. But when you do it for 1,000 times or 10,000 times, it's hard to get 10,000 tails and then 0 head. So it will approach into half and half. So your experimental probability will approach to the theoretical probability when the n approach infinity. Like you get your n to large enough. Okay, your n is large enough. So it's called the long run proportion. Okay, long run proportion is the experimental probability for a sufficient large number of trials. What is sufficient large number of trials? Like, I don't really know, like the particular number, different experiment in different like trials. But like I said, it's a really large number. Okay, the more the better. So infinite many, the more you do, the more approaching to the theoretical probability. So that's the basic definition for probability. And I have listed all the formulas here. I think, okay, this is all the did I miss one? I'm not sure. Like, let's go through them. So first of all, a single event like A, probability A, well, I'll give another restriction here. It needs to be less than 1 and greater than 0. Okay, probability A is less than 1, less than 1 greater than 0. So in between 0 to 1 for any event. Empty set, probability of empty set is 0. Okay, there's 0 chance to get that. So there's nothing in it, so probability is 0. So for probability of the sample space is definitely 1 because it has include all the situations. So it must be 1. So it's called the sum of the probabilities of all outcomes of a random experiment. So probability A dash is called the complementary. Okay, it's the complementary events. So we have A or we have not A. So A or not A. So 1 minus the probability of A, it will be, the rest will be not A. So the add up should give you 1. The next one is the additional rule. Probability A union B is the probability A plus probability B and minus the intersection. Okay, minus the intersection A intersects B. So that's the additional probability. Next one is really important. The next 3 is really important. We use that a lot. So probability A intersects B is 0 if, okay, if there's no intersection between two events A and B. Then event A and B are said to be mutually exclusive. Okay, it's mutually exclusive. What's mutually exclusive? In a Venn diagram, not that, that's with intersection, that's A, that's B. They are mutually exclusive. So, which means events cannot happen at the same time. Let's say we can have daytime and nighttime. They are mutually exclusive events. You can't have daytime and nighttime together, so they are mutually exclusive. Something can't happen at the same time. Okay, they are called mutually exclusive. The formula we use to test, well, if ask you to prove something are mutually exclusive, you need to show me probability A intersects B must be 0. For example, I give you event A equals to 1, 3, 4. Event B are 2, 6, 9. So what you say is A intersects B is an empty set. Right? There's no intersections. So probability of empty set equals to 0. So probability A intersects B equals to 0. So they are mutually exclusive. Well, you know, questions normally we have in VCA exam, they're not going to describe things. They're not going to describe like daytime, nighttime. They will all normally give you numbers. Okay, when you see numbers, you need to go through calculations like this. Okay, you need to go through calculations. You need to actually show A intersects B is 0, and then you make the prediction that this, you make the conclusion that they are mutually exclusive. Okay, that's the first thing. And the next one I will talk about is, okay, I missed this formula here, is the given. Just add another formula here for yourself. Probability A given B. Okay, when you will know like it's a given situation in the question, there are words indicate that, well, there are some situations there's no indication words, but like you can feel, okay, that something already happened and ask you to calculate another probability. But like normally there will be some words like, say, given that, knowing that, well, knowing that in this team there are more than 4 girls already, and calculate the probability there are less than 10 girls. Okay, so knowing something is already a pre-knowledge you have. So that's the given, that's the event B. Or if, okay, the word if also indicate a given case. So given that, knowing that if something or something happening, okay, something happened, and then find the probability of what. You can see the language already indicates something already happened. You know something already happened, then that's the given case, and that's the event B. And then you're going to calculate event A. So what's probability A given B equals to? That equals to probability A intersects B over the probability of B. Yeah, probably A intersects B over the probability of B. So that's another formula I missed from this list. So that's a given situation. Okay, you need to remember this formula. It's very useful later. So all of the formula I list here, we'll learn quite complex stuff later for probability. But these are all the things we have learned in the past 3 years, and they are still useful. Okay, they are still correct formulas. Doesn't matter what we learn later. They are always correct. So this is the conditional. This is called the conditional probability. Okay, they are the conditional probability. Okay, next thing we'll talk about is independent events. Okay, independent events. This is mutually exclusive. Okay, what are independent events? Independent events are the events are not influencing each other. So for example, what you wear today is not going to influence what I wear today. Okay, you have no influence on me. Okay, so we are independent. What we wear today is independent events because it doesn't matter what you did, it's not influencing me. So that's independent events, but that's only understanding. Okay, you understand what is independent, but what's the formula shows you that they are independent. So the most original formula for independent events is this one. So probability A given B is still equals to probability A. That's the most original formula we talk about when we talk about independent probability, because given you B happened already, ask you to calculate A, that still equals to probability A. That means there's no influence. Okay, so you know B happened, you are asked to calculate A, but that is still equals to you just calculate probability A, which means there's no influence between A and B. So that's the most original formula, gives you why they are independent events, because telling you B happened, ask for A, that still equals to original probability. But we know we can do something more for this formula. This is not the common one. I'm pretty sure you won't recognize this as the most common one like we use for independent events. So if I can expand the formula on the left hand side, because I've talked about the conditional probability already, so I'll expand the formula on the left hand side. That gives me this. Okay, probability A intersects B over probability B, that gives me probability A. So I can times prop B on both sides of the equation. That gives me prop A intersects B equals to prop A times prop B. That is the other formula to test whether they are independent or not. Okay, that's the other formula to talk about the independent, whether they are independent or not. Okay. So you can use this one to test whether they are independent or not. When you test whether they are independent or not, you need to calculate the left hand side first, then right hand side. Okay, so you gives me what's the probability of A given B, and you tells me what's the probability of A, and then you said whether they are equal or they are not equal. Then you make the conclusion, this is independent events or they are not independent events. But you can't start with this formula. Okay, you can't write this formula at the beginning. As soon as you write out this formula, which means A and B are already independent, but at the beginning you don't know whether they're independent or not, you need to calculate them separately and then compare them. So same as use this one, you need to calculate the left hand side and then right hand side and just compare whether they are same or not. Okay, so give you an example. That's a VCAL question, I remember. Give you a sample space with 1, 2, 3, 4, 5, 6, 7, and then give your event A. Event A is 1, 4, 7, and give your event B. This is a really random question. 2, 4, 7, 2, 4, 6, 7. Okay, and I ask you whether event A and event B they are independent or not. Well, you know why I give you situations like what you wear, what I wear, you can see they are independent. But how about if I give you numbers like something like this? How you can decide whether A and B are independent or not is totally through the formulas. And you can see if I use the given formula, it's quite difficult to do. So I will use this formula instead. Okay, I'll use the bottom formula. This is a common formula. Okay, the bottom one is a common one. So I will find A intersects B first. A intersects B gives me 4 and 7. Okay, and then I'll find prop A intersects B. You find A intersects B. Probably A intersects B is 2 over 7. Okay, 4 and 7, there are 2 in set A intersects B and there are 7 in the total count. That's 2 over 7. And then you calculate prop A times prop B. So prop A is 3 over 7 times prop B is 4 over 7. That gives me 12 over 49. And the conclusion I can make is prop A intersects B is not prop A times prop B. Okay, that's when you make the conclusion. They are not the same. So A and B are not independent. Okay, they are not independent events. Okay, this is one question in multiple choice. They give you some situation like this. They give 5 situation like this, and they ask you which one are independent, which one is the independent events, and you need to test all of it. Okay, like you need to do this 5 times. That's the multiple choice. So they are not independent events. That's the full proof. How you should make the proof. Okay. Another thing I want to ask you is, do you think mutually exclusive events is independent events? Or do you think if the events, those 2 events are independent, they will be mutually exclusive? Yes or no? Basically what I want to say is mutually exclusive events and independent events are the same? Will they happen at the same time? Okay, they are not the same thing. Yes, they are not the same thing. But will they happen at the same time? No. Okay, and the answer is no. Why not? For mutually exclusive, you want A intersects B equals to 0. Right? You want that equals to 0. Okay, if they are mutually exclusive, that's 0 already. But if they are also independent, A intersects B equals to A times B. Okay, can you tell me how probability A times probability B can be 0? How? Like give me one possibility how A times B equals to 0. Either prop A to be 0 or prop B to be 0 or both to be 0, right? When you said the probability is already 0, which means that thing doesn't happen. There's no such event. Okay, it's an empty set. There's no such thing happen. So you already just only have one event. So it's not true. Okay, it's not true because they require different things. For mutually exclusive, it requires the intersection to be 0. But for independent, you require A equals to A times B. There are some values. So they will never happen at the same time. Okay, they will never happen at the same time. So it's hard to understand why mutually exclusive they are not independent or why independent are not mutually exclusive. You can think about this. Independent means they are not influencing each other, but they still happen at the same time. So what you wear and what I wear, like say you wear black or I wear red, they are independent. Okay, totally depends on what we think on this day. But they can happen at the same time. Okay, you wear black, I wear red. They can happen at the same day, but they can't be mutually exclusive because they can happen at the same day. Then it's not mutually exclusive. So that's why they are not really the same thing. Okay. The last one is the law of total probability. So this one I think you saw this in year 11, but you don't really use it. It's still in year 12. You don't really use this one. This is basically a tree diagram. Okay, this is basically a tree diagram. So probability A equals to what? Probability A equals to prob A given B times B, and probably A given B dash times B dash. It's not really that helpful. Okay, it's not really that helpful. You can use tree diagram to get this done. Okay, it's totally tree diagram. I'll show you example for the next page. Okay, in a certain town, the probability that it rains on Monday is 0.21. And if it rains on Monday, then the probability that it rains on Tuesday is 0.83. If it does not rain on Monday, then the probability of rain on Tuesday is 0.3. Okay, can you see this? If I use M and M dash to represent it's rain on Monday and not rain on Monday, if I use T and T dash to represent it rains on Tuesday and rain not on Tuesday, so I use this to represent. Okay, rain on Monday, not rain on Monday, rain Tuesday, rain not rain on Tuesday. So So what I will have is, if it Monday ring is 0.21, so it's probability Monday that equals to 0.21. If rings on Monday, okay, what if given, okay, given conditional probability, then the probability it rings on Tuesday is 0.83. So probability ring on Tuesday given Monday rings equals to 0.83. If it doesn't ring on Monday, then the probability it rings on Tuesday. Okay, so that will be this. You should learn how to write things in the correct math notation, because if you can convert the words into math notation, you can definitely get the question right. Okay, if you can get all this into the math notation, you will know what you should do. So probability given and not ring, that probability is 0.3. So for a given week, find the probability it rings on both Monday and Tuesday. Okay, rings both Monday and Tuesday. So is probability of M intersects M intersects T. Okay, Monday and Tuesday ring. So Monday intersects Tuesday. That equals to what? That's equals to prob M. Okay, Monday ring times the probability Tuesday ring. But Tuesday ring depends on whether Monday rings or not. So that will times prob T given M. That is the probability of Tuesday ring by knowing Monday ring already. So that's both Monday ring and Tuesday ring. That gives you 0.21 times 0.83. Okay, I'm not going to do the calculation. You can do that. Okay, for B, ring on Tuesday. So you want to find the prob T. Okay, I want to find the prob T. Ring on Tuesday. So, by using the conditional probability, total law of probability, I can write this formula. Okay, you can see the thing on the previous page. I want ring on Tuesday. So it can be Tuesday ring given Monday ring times probability Monday ring plus probability of Tuesday ring given Monday not ring times Monday doesn't ring, the probability. So that's the total law of probability. So what I will have is, here we have 0.83 times 0.21 plus 0.3 times Monday not ring is 1 minus 0.21. Monday ring is 0.21, Monday doesn't ring is 1 minus 0.21. It seems quite complex, but if I can do this for you, you can see what I'm doing. Tree diagram. Monday ring is 0.21. Monday doesn't ring is 1 minus 0.21 is 0.79. Monday ring gives Tuesday ring is 0.83. Monday doesn't ring, give Tuesday ring is 0.3. So I can also complete the rest, 0.7 and 0.17. Okay, it's totally tree diagram. And then you can see, okay, Tuesday ring is 0.21 times 0.83, 0.79 times 0.3. Both Monday and Tuesday ring is the first outcome, 0.21 times 0.83. So it's just the tree diagram. Okay, so the total law of probability is just the tree diagram. You can, if you can set up the tree diagram, you can see everything. Okay, you can see everything. Next week, remember to bring your calculator to class because we will do a lot of calculations. Can't do that by hand, so make sure you bring your calculator. The last thing I want to talk about today is the 3 diagrams. Okay, so we have Venn diagram, tree diagram, and the Kano map. The most important one is this one, and then second is tree diagram. We don't really use Venn diagram that much now. So number 1 is most important. The Kano map is most important. And you know that's the AA-BB-. There's only 2 events happening, and you can find the middle 4 is the intersection. And the rest is total. So total probability is always 1. So the right corner is always 1. Well, I think you know how to do this, and I know how to do, you know how to do tree diagram, and I think you know how to do Venn diagram. So I'm not going to show you those 3 graphs, but can you try the example below here? So this example is actually a VCAL question. Okay, that's in the part 1 exam, and it's the VCAL question. You can't believe how easy is that. That's actually 3 marks, or I think it's 3 marks for this question. Like you can see, that's free 3 marks. Two events, A and B, for a given event space. Prop A is 1, 5, prop B is a third. Calculate A dash intersects B when A intersects B is 1 on 8. You can use Venn diagram or you can use the Kano map. You can choose any. When you finish, you can have a look. You don't need to complete the whole table because it's not enough information given. You can't finish the whole table, I think. You don't need, okay, I think you can. Okay, I think you can, but you don't need to finish the complete table. You just need to see where it's asking. So the pink circle there is what it's asking, A dash intersect B. You just need to work out that spot. This also can ask like as number 3. So calculate prop A dash intersects B when A and B are independent. You can ask this as well. So when you know it's independent, you know prop A intersects prop B equals to prop A times prop B. So it's 1 of 3 times 1 of 5. That gives you 1 of 15. So you change this spot into 1 of 15, and then you can use a third minus the 1 of 15 to get the pink circle. So it's the same. Like I think it's asking somewhere before as well. So that the types of questions you can have for economet. But normally they won't give you that easy questions on VCA, like it's too obvious, okay, it's just too straightforward. Most likely this table can be used within a question, okay, within a big question like the exam response, and in one part you need to use the economet to work out a particular probability. Any questions for what we have learned today? Okay, if you don't have any questions, we can stop here, and Monday we start to talk about discrete random variables, which is a really important exercise. This is all the revisions, okay? Make sure you remember all the formulas and know the meaning of it and how to use it. Okay, so you can do some exercise for 13A and B, okay, for 13A and B. No more questions?